All right. So thank you guys for joining me on this weekly meeting. So there's actually no particular monthly development cycle agenda for this week, but it was mostly for me. It was mostly a lot of cleaning up for the 0.3 release. I did a refactoring on TD3. Actually, figure out a bug that was associated with the previous implementation of TD3. And also perfected a lot of utility scripts for submitting runs or just using AWS or using Docker to run the experiments. And also Rosalind has been working on basically refactoring the soft actor critic. Yeah, let's take a look. So Rosalind, is there any particular environment that you ran the SAC on?
Let me check real quick.
Oh, I think I see. So for example, Hopper, right?
I think it's best if I will save the report I have opened here and you can.
Okay, yeah, that sounds great.
It's called the SAC comparison, SAC comparison.
Yeah. Okay. Yeah, let's take a look. Okay, so SAC is actually performing, definitely performing very well, and that is the case with Hopper as well, it appears. And TD3 is still very good. Okay. Yeah, very nice work. Yeah, so in Humanoid, actually very good. But I haven't had a chance to. So some of the run crashes, and I would have to rerun them. But overall, I think it looks very good, Rosalind.
No problem.
Yeah, thanks for the nice work. So before the end of the meeting, I might ask you to sort of do like a maybe just a short talk on what kind of modification did you do to the SAC so that it has this drastic improvement for the performance. But I just want to quickly go over basically some of the things I did for the infrastructure and how the scripts are going to be run from now on for doing benchmarks and stuff. So basically, I wrote up a couple utility scripts. The first one is to generate experiments. And by using this benchmark.sh, I can essentially generate a lot of scripts that will be used for submission to AWS and actually run experiments. So one example is something like this, where I say I want the gym IDs to be these IDs, and I specify weight and biases project and weight and biases entity, specify the desired total number of time steps, and I just run it, and then it'll generate something like this, which you can just copy and paste and just run it in your terminal right away. But also, I wrote a script to sort of parse through these and just submit it either through Docker or through AWS. So that's where this benchmark submit.sh come in. And I just have a variable over here that says submit AWS equal to false. As an example, you can just run this without the submit AWS. And what it's going to do is to print out a bunch of Docker commands that you can just run. So Docker, for us, is basically a really good abstraction because you can use AWS, you can use Google Cloud, you can use anything you want, any server you want, as long as you can run this Docker command, and then you'll be able to reproduce the work or run the benchmark. However, since I am personally using AWS for all of my experiments, what I do is simply just add another command that says submit to AWS, and basically I can just run all these, and then all of the experiments will be queued in AWS batch, and we basically see all of the results. And when some of the experiments fail because we use a spot instances, which is ephemeral, which means some of the instances could be terminated because AWS needs its computational power back, and they just kind of terminate my instance, which is okay. But essentially, we need to get a list of the runs that are crashed or terminated by AWS, and then just resubmit them. And we do that by saying this is the project. Clear out the benchmark has some crashed runs, and then I'm just going to rerun them and resubmit to AWS. And the idea is that eventually, if you're left with some runs that you just can't get AWS to work, then you go back here and then you just don't say submit to AWS and just run it as Docker command using your own computer, and you'll be able to make sure that the runs will finish. So that's basically the infrastructure part that I did. This will make it easier to run a lot of experiments in the future and make the process in general a lot easier. One additional thing, was to do a refactoring on the TD3. So in particular, there was actually an error with the existing code. So let me go ahead and show you. So basically, in the TD3 implementation that I had before, I didn't actually use the target actor at all. So it was all of the components in TD3, and the target actor was basically not used. Let me see if I can find that. All right, so it's this file. And then Right. So over here, right, I get the next state actions. Notice it's the actor.forward instead of target actor.forward. So anyway, so this is a bug that is being fixed. And in the newer version, when you get the next state value, it should be target actor. Let me check the newest version. Yeah, the newest version is saying target actor.forward the next day. So the target actor is actually being used. And even though in the previous experiments that doesn't seem to hurt the performance a lot, but this is considered to be a more correct implementation. So anyway, so those are mainly the two things I've done for this week. So Roslyn, would you like to give a demo or a really short talk or long talk, whichever you prefer, to talk about what kind of modification you did for SAC?
Yes, I will. I'm trying to bring up the screen right now.
Okay, sounds good.
How do you do this again? Yes.
How do you do this again? Love it. I really like how in Hangouts, I don't have to terminate my sharing screen and then Rosalind can just start sharing his screen. Because I think in Google Meet, which is the new transitional, the service that Google is trying to transition Hangouts into, they don't allow two people to present at the same time. But anyway, could you make the text even larger?
Sure.
Thanks. I think this is good.
Okay. Well, at first there is just hyperparameters reworking. But here I augmented the buffer size a little bit just to be sure. And well, I don't know if you remember the Dennis Yarat's implementation. That one who was supposed to be really fine-tuned, right? And one special technique they use there is to delay the target network updates.
Okay.
So I added the parameter for that, but actually I did not use it in the CleanRL benchmark yet.
Wait, so I thought the target network is always being updated by using tau, right? Why is there a target network frequency?
It's not only the tau, but also the interval at which it is updated.
Okay, I see. I see. Okay.
Like two parameter to tune. Actually, from some earlier experiment, it does not seem to change the performance that much.
Okay.
What is actually more interesting is, like in TD3, they delay the update of the actor network.
Yes.
Right? So I also added the maybe I did not add it here. Probably.
So
yes, it's a policy frequency, right?
yes, it's our. I'm already seeing it. It's in the bottom
Yes.
part. Yeah.
Yes.
Okay.
So a few experiments I have actually shown that this is one of the most important, like not fine tuning but trick when it comes to TD3 and SAC. Okay, so other things here I separated the loss, the policy, and the Q-value loss.
Okay.
Instead of using the same one. Well, it's most of the implementation do it as it is, but I don't really know the reason.
Okay.
Also added just some weight initialization to Xavier and zeros for the types.
Okay.
And then we enter the main body does not change that much.
And is the weight initialize scheme the same as did the other person's implementation also uses the weight initialization scheme, or is that something that you did for your experiments?
Let me think. I know that the original offer uses Xavier.
Okay. Give me 1 second.
Dennis Yarat's, I am not that sure. I will check real quick.
Okay.
The user, okay, almost got it.
Mm-hmm.
They use the orthogonal initialization for convolutional neural networks.
Could you put it on the screen that you're sharing? I want to
Yes.
I want to see what it looks like.
I will have to change the window again.
Okay.
Here is the, well, there is this function.
Okay, I see. So sort of similar to how
PPO.
yeah, exactly. How PPO do the weight initialization. Okay. So basically, a bias 0, and then orthogonal. What is... So it would appear that it uses orthogonal initialization with the default scaling. And what is the default scaling? Do you know?
No, I do not remember that one.
Yeah, because I know that in what's it called? OpenAI baselines, they have different scaling for essentially different layers. For the hidden layers, they have one scaling, and for the output layer, and they have a different scaling. Okay, so the default one is 1. Okay. Okay.
Yeah. Well, the scaling game. Right?
Yeah. It is a game. Yeah. So it's equivalent, I think.
Here they say actually it's like for convolutional neural network. And but there is linear only. And I am pretty sure this is the function where the function waits in it.
Okay.
In the file util, right? File, which is called in that's the function they call.
Okay, I see.
I would say that's what they do. But overall, the initialization warrants some.
And it's also interesting, right? Did you see their log STD? It appears he's doing something kind of special with it, right? It has log STD min and log STD max.
Mm-hmm. Yes,
and the log STD is sort of being bounded by the max and min. I think that's what the operation is trying to do.
This is also present in the OpenAI spinning up implementation, and that is actually why I incorporated in this file too.
Okay.
Only at this part.
Nice.
Instead of using the clamping.
Can't see that right now.
Oh, yes.
It's on the other screen.
One nice feature of Zoom is that you can share only one screen at a time, but unfortunately.
Mm-hmm. I don't know. I don't like Zoom's interface that much, but anyway.
Yes, this part we do like the reshifting of the log STD distribution.
Okay.
Kind of.
Okay.
One
Nice.
thing that I always wonder why do the tench just before doing the shifting.
Well, 10 squashes things from any range to -1 to 1, right?
So, but if you're already reshifting.
Yeah, I see what you mean. Yeah, I don't know. And
Actually,
what is it exactly trying to do, right? It's log std max minus log std min times log std plus 1. What does it even mean?
So the mean is -5 plus half.
And when you have log, you have the log rules, right? Log minus another log is log of 1 divided by. It's essentially log of max divided by min, right?
Indeed.
Yeah, and then that. Yeah, I don't know. I'll have to look. This is something that seems really weird, yet maybe important.
Actually, if you could bring up the SAC comparison report really quick.
Uh-huh. Do you want me to open it?
Yes, if you don't mind.
Yeah. Okay. Yeah, it's open right here.
Orange line. No, just the first one is already enough. The orange line is actually the one corresponding with the log std clamping.
Right? Okay.
The yellow one is the one with this kind of district log std trick.
Okay, I see. Yeah, I think we should ask them about it. See, is there kind of any motivation behind it? At least to know why it has this kind of weird formula in it.
Indeed.
Yeah.
In any case, the rest does not change that much. Another noticeable aspect is that I enlarged the hidden layer.
Okay.
And actually, it seems to quite matter.
Really?
For the 128AT, it gets way worse performance. But maybe do some ablation later.
Yeah.
We will see. And replay buffer here, I think beside the neural network, also added the auto-tuning of the entropy. But honestly, I don't see the use that much.
Okay.
Oh, wait, actually there is one potential use for such method.
I think we still should try to use the Autotune by default because, that is sort of being, whichever is implemented in the newest method, right?
Yes, indeed, most implementation use the auto-tuning anyway. So.
By the way, I also noticed that in that comparison that you had right there, if you go to the very top, that is not the one. Yeah, if you go to the very top, I'm actually surprised to see that TD3 and PPL perform similarly because in the original paper of TD3, Hopper is an environment that TD3 significantly outperforms.
Well, first, I'm pretty sure they do it on the Joko version.
This is the Majuko version, right? Actually, in the Majuko version, TD3 is performing worse.
Wait, I do not know if I have run the most updated version.
That is the most updated version.
No, this is SAC continuous with the clamp action. The yellow one is the most updated version.
I see. I meant the comparison between TD3 and PPL, not the comparison between the SAC.
Okay, let me check real quick again.
But that's sort of a side note. Maybe that's something that we can revisit later. Please continue with the SAC implementation.
So the Autotune seems to be quite handy in environment with the hard exploration.
Okay.
So here it's the mountain car, right? Quite easy actually.
Do you see that seed importance? Really important.
Yeah, actually, this is due to this. I have quickly mentioned it before. Here is the stuff. I don't know if the zoom level is readable enough. But this is worse.
Yeah, 100 is fine. I think it's fine. I can see everything.
So here, SAC DU is like delayed update for the actor network, right? And it's one of the run which gives the best performance.
Okay.
Actually. Not the greatest, but well, the best in this set. And the first seed actually reaches the like almost ideal performance, right? Second one is working, for the lack of a better word.
I see. But could you see the actual training the video? I want to see what it. Do you know which one does it correspond to?
The video.
Yeah. You just have to go into it. Yeah, I'm a little curious. Okay. Wait. Can you go back to the end? I think it still learns. It's just they're doing it very slowly, right? See? Oh, never mind. Maybe not. Okay, never mind.
Well, after 1 million, if that's the best you can do, not worth much, right?
Right. Okay.
So I was wondering why on such a simple environment the standard soft actor critic was not working. Here it is denoted in the blue line. So next I made some experiment with the alpha to encourage it to explore more. And one good thing is that Autotune seems to solve this problem. Wait. Oh, so it was not Autotune. Surprisingly, it's soft actor critic without any exploration that manages to solve it, kind of.
Okay.
And I'm pretty sure there's also the importance of the seed, probably.
I see.
So the first seed gives a good result,
and the second seed
is
really
probably bad. What brings it down.
Right. Okay, I see.
So there is that Autotune. I think there's also a few experiments. Overall, it's not too bad, the Autotune here in gray color. But I guess it depends on the environment.
I see.
Oh, actually, one of the environments, the default soft actor critic does not seem to work well is half cheetah variants. I think even the Mojoko version, there is this like really slow updates. Just a second, I will remove the.
By the way, I see you have that sort of importance of different parameters set up. So how did you set up that?
Which one? This?
Yeah.
It's a parameter importance.
I see. Yeah, it seems to be. I never used it, and it seems to be very important, actually.
Yes, it might give some good insights.
Yeah, actually, it does.
Using it yesterday. I think soft actor critic kind of learns the policy that has the head of the cheetah always down. Right. Submissive policy. Maybe that's why. But this auto-tuning seems to actually mitigate the problem of standard soft actor critic. Here again in blue color, not learning quick enough. But I guess more are still needed. So this is auto-tune, right? Auto-tuning.
I see.
Seems to work.
Yeah. Okay.
And back to the source, I guess. We do. Yes. So after the auto-tuning, I also added learning starts. parameter to collect a little bit of data. The rationale is, according to the few papers I have read, to have some data and to train especially the Q-value network over a wide enough state action pairs, so it could have a better less biased. Because if we start with a suboptimal policy, really, it will probably tend to explore only bad parts of the environment, and thus the Q value itself is impacted.
I see. I see.
It's a little, quite a bit important details. Hopefully, I can do some appellation regarding to that, but that's for later.
I see.
And beside that, I think that's pretty much it. The training logic here does not change for the Q values. For the actor, there is this loop that allows to separate the actor update interval, as in TD3.
As in TD3, right. So it turns out, basically, it seems the case that a lot of things in TD3 are sort of also useful to SAC, I guess.
And I would say it could extend to most actor critic methods. But this is just an hypothesis. English broken.
Okay.
Okay. Just to back this up with some concrete experimental evidence, we are back to 1 dB again. So here is the humanoid bullet environment, and just a second. So in light blue or cyan, actually, we have a soft actor critic with delayed update of 2 for the actor critic, for the actor network. So we wait every 2 updates, we update the network, and here is with 4 updates. And also something that TD3 probably does not. Once we wait, let's say we have 1 million step, right? And we delay the actor update by 2. So it means that the actor network will be only updated basically 1 million divided by 2, right? So in the current version of the source code, I added something to compensate. So although we update only every 2 time step, we do it twice. And if we update every 4 time step, we do it 4 times, kind of. Okay. To compensate. And actually, the performance seems to be quite, already better than the standard one. As the cyan version here is really taking the lead. And this trend can also be observed in a few other environments, Humanoid 2, for example. This is actually where soft actor critic performs the best. I don't know if you have noticed already, but
yeah, I think Humanoid is one of the environment that SAC, I think it really stands out. Let me see. So if right, Humanoid is actually not one of the domain tested in the TD3 original paper. I don't know what was the reason behind not testing it, but
interesting.
Yeah, indeed, interesting.
Yes, but that's pretty much it. I try to rework the logging logic little bit, but I guess you can probably see the pull request.
Yeah, sounds good. Whatever you're ready. Yeah, I know. Oh, right. Let me see. Oh, so I think one comment that I have right away is if you go to the very top of your script.
The file?
Yeah, sort of where you define the time limit thing. If you go down a little bit, I think. So notice, since you're using different kinds of way to do all this, I think going from assert env time limit to env equal time limit from line 119 to line 125, those lines will not be needed, I think. Yeah, since you're not using the args episode length sort of as the
Yes, for like
for
how
the
many
loop.
times we sample, right?
Right, right, right.
Yeah.
Hmm.
So this is basically bye bye.
Yeah, I think so. Yeah, and I think it makes the script more uniform. I think.
Indeed. I was always kind of reluctant to discuss the time limits.
Yeah, yeah, it's a
But
little
you
hacky.
gotta do what you gotta do. I understand that.
Yeah, yeah, it was a little hacky. And I think basically the newer version for the 0.3 release doesn't have this ugly hack because for the PPO where you have batches, it's handled essentially by the vector env. And for DQN sort of value based methods, then you're just using this sort of for loop, which is pretty good.
Yes, exactly.
Yeah.
Okay. So,
I mean, by the way, if you want, I think what you should do is also potentially write a blog post like I did with the PPO and just to write, I don't know, 20 implementation details with SAC and just basically write out a bunch of things that you're writing, right? For example, the log STD max, log STD min. I wonder if that could be used for PPO as well to improve the continuous action space.
well, for PPO, I'm pretty sure the log std is a fixed parameter.
Yes, yes. However, you can always do it the same way as you do in SAC. Just generate it as depend, so that the log standard deviation is dependent on the states. Which by the way, I think is one of the things that is studied by the PPO paper. Well, the later PPO paper that does the large empirical study. I think they compare it and they concluded that it doesn't make much of a difference, if I
The
remember correctly. So
PPO,
so it's what matters in on policy reinforcement learning, a large scale empirical study. Let me try to find that real quick. So if I just search for so right, there also appears to be no benefits if the standard deviation of the policy is learned for each state, outputted by the policy network, or once globally for all states. So that's this, right? If you look at figure 23, look at my screen. Analysis of choice of global standard deviation. So global standard deviation would mean the standard deviation is parameterized as state independent. So that would be the implementation that is currently done for the standard deviation of PPL. And then if you're not using global standard deviation, then it's the same thing as SAC does. And it would appear there's no noticeable difference, right?
indeed, in this case, there is none. I would like to make something like to check if there is anything related to entropy and the PPO in that paper. Do you happen to have seen something like that?
Entropy and what?
Entropy in the
There
PPO.
is, there is. It's very well done. It's very comprehensive. So that happens in the regularization methods or soft constraints. Right. We do not find. So it's basically this: a regularization. We investigate different policy regularizations, which can, in a form of penalty bonus for higher entropy, and they basically say we do not find any evidence that any of the investigated regularizers helps significantly on our environments, with exception of half chata, on which all of the constraints, especially entropy constraint, helps. Right. So this is what would happen. I would imagine, if you look at different regularizers. So in Hopper, as an example, this is no regularization, and this is with the entropy penalty. So it doesn't really do much.
Okay. I am pretty sure
Except in half chatter, of course. But
it seems there is two approaches to entropy in this case.
Yeah. I'm not exactly sure what that is. Constraint entropy?
No. What I was going at before is like entropy as in the soft actor critique, where on top of the Q value, we also
I see.
find the entropy of the policy itself, not the entropy constraining of the loss.
Right. Then it's different things. I don't know.
This is done to encourage exploration, right?
Right.
And a more in soft actor critique, especially a more exploratory policy will be the one, since it's parameterized as a quotient policy. It's a policy that has the standard variance high enough, right? So the log STD parameterization will probably be more related to the entropy maximization of the policy itself instead of the constraint.
Okay.
And therefore, that's where maybe the state-dependent log STD as well as the shifted log STD might play an important role, I would say.
I see. Okay.
I'll try to look into that.
Yeah. It's interesting. So especially since, if the log STD formulation doesn't matter whether it's global or state dependent, it might be also interesting to experiment the sort of what's it called, the log STD trick that is used in the SAC implementation for PPL. But I suspect it's probably not going to make a lot of difference. Anyway. All right. And that's good. I want to check the performance of something real quick. So we have Hopper. I'm just kind of surprised in a lot of the domains we compared, TD3 doesn't seem to perform a lot better. Which is, for me, is counterintuitive.
Those are discrete environments.
Right. So let me duplicate this real quick.
Well, you're already in your versions.
Yes. So I want to check something else. So if I check Humanoid, right, that's a domain that, right, it really shines. I want to check some domains that really performs well as claimed by the TD3 paper. So one of which is Ant. So is that the case?
Is there?
Yeah, okay, so that makes sense. Ant performs very well in TD3. And another environment is Hafcheta. I have a TD3 paper open somewhere using my iPad, and I can see. Okay, so SAC also TD3, right. SAC TD3 performs very well. That makes sense. And yeah, I think that's basically it. That's the two domains that it really shines. Well, I guess the other one really is Hopper, but as we see in the beginning of here, it doesn't really perform that much better than just PPL, I guess.
Well, also, please note that is the not updated version yet, and there is a one.
Yeah, they're using Hopper 1. We're using Hopper V2, but still.
Okay.
Yeah. Yeah, well, and also, I'm looking at original paper. So in original paper, PPO reaches around 2,000 reward for Hopper. And using TD3 reaches about 3,200. And that is, well, the case kind of over here, but not a case over here. Oh, excuse me. Also, TD3 is run for only 1 million time steps, and TD and PPO is this is for 2 million time steps. Anyways, some minor deviations.
Interestingly, I have some experiments over on my side here on the Hopper logic, right?
Mm-hmm.
And yes, basically the version that incorporates the TD3 trick, namely the actor network delayed update, is the one that is performing the best and almost reaches 3000 too.
Mm-hmm, mm-hmm.
But the default one is also not too bad.
I see. Okay, nice.
And what was the other one? Half cheetah.
Yeah, half chata.
I am not sure I have added those experiments yet.
Okay.
Yes, I only have the bullet and variants.
Mm-hmm.
For next time, I guess.
Yeah. Yeah. So I would say keep tuning SAC, and I'll try to finish the benchmark, and we can just basically do a 0 point release, or we'll print out sort of every benchmark we have. So I think we should probably not work on A2C. Because as mentioned, I think A2C is a special case for PPO. It's interesting to just left it there, but sorry, yeah, it's just not worth the effort to re-implement it. But unless of course, in the future I have more time, I think maybe we should do that. But otherwise, I'll probably basically releasing PPO, DQN, C51, DDPG, TD3, and SAC. So that will be the main algorithms we'll try to push that are high quality and benchmarked in a lot of different games.
Sounds good to me.
Yeah, and right. So I actually have a friend whose PhD student seems to be interested in. He graduated. Whose PhD student seems to be interested in doing some curiosity-driven learning, which I know you, Ross. I know you are very interested in, and I'm very interested in. And I was asking my friend if his student would be interested in leading a monthly development cycle, but he hasn't got back to me yet. But anyway, I'll keep you guys posted on that. Yeah, but otherwise, so for the next week, is someone willing to sort of organize a meeting, sort of presenting something? Because I probably will not be. I'll be just sort of be having my vacation.
I can't.
Okay, you say you cannot, right?
Yeah, I cannot. Yeah.
Okay. I mean, we don't have to keep the meeting going on if if we don't have people to present their present things. But if you have anything interested, if you have anything you would like to present in the weekly meeting, please let me know, and I'll just put up a link in the channel once the 5 p.m. EST on Friday starts, and I'll probably join, but I probably just won't be contributing as much.
It is starting next week? Or...
Yeah, starting next week, I would say.
Okay. I'll keep that in mind.
Yeah. I'm not sure. Maybe next week will be the last week, but I think for now this may be the last week. Anyway, does anyone have any questions or comments? If we don't have any
questions,
yeah, go ahead. Go ahead.
No, I don't have any questions from me.
Okay.
So So once you guys are back after vacation, maybe we can start with the next thing.
Yeah, I know. I definitely want to push forward the curiosity-driven learning paper, and additionally, I think something interesting would be to look at the what's it called? I think I want to implement Impala, or not so much as Impala, not so much implement as to sort of copy, because there's. I think I probably mentioned this before, but PyTorch has a very good implementation on Impala that is very well benchmarked, and it runs very, very fast. And I think it will be very helpful for my research if I sort of bring it in. So that's just something that I'm considering. But probably more interesting for the implementation sake. I think Impala and curiosity-driven learning are both interesting. By the way, does anyone have any particular algorithm that they're interested in looking into?
For example, recently I was looking over the A3C, and you mentioned Impala just before, and I am pretty sure that one has also some distributed component to it, right?
Yes, but right now I think about it, there's no reason to implement A3C, right? Because Impala is better, I guess.
Yeah, well, it's better. I guess if you want to seriously implement it, the distributed part will be quite a challenging. So having a goal,
I wouldn't worry too much.
Is simpler. Could be a learning experience, at least.
I don't think implementing, well, yeah. So for the main part, I know I would not be implementing the distributed part, because that is a much more complicated
or
quest.
Can Impala work non-distributed?
Yeah. So that's why I like this about this library. It has this single file, well, mostly single file implementation on Impala. It's about 600 lines, and the code seems very readable, and it uses some multiprocessing to basically do the job, and it has apparently higher throughput, data throughput than A3C. So overall, I think it would be more worth the time with Impala.
I see.
Because if you look at a paper, it seems very complicated, right? But if you look at the TorchBeast, the repository, it seems quite simple. We provide both a pure Python implementation, MonoBeast, as well as the multi-machine high-performance version, PolyBeast. So the pure Python implementation, as I showed a second earlier, seems to be very readable. I think it's very promising, and I think I would be very interested in adapting it and, for example, using it for my own research.
Roger that. I'll try to have a look at it.
Yeah, and if you look at its comparison, right? For example, with A3C, it's remarkable. Oh, sorry, it's not this paper, but it's from the. If you look at an Impala paper, and they have somewhere over here, essentially this is how fast your algorithm runs. And with A3C, it runs for 65K. So using 64 CPUs or 48 CPUs and 1 GPU, it goes for 13K time steps per second. And using Impala, it's about twice as fast, I guess. And if you use the distributed version, Impala, is much faster. But it's also the performance, right? It's not only the how fast you can go, but it's also the performance. I think in a lot of games, Impala basically performs much better than A3C because A3C is a strictly on policy update. So while Impala it can handle the stuck the delayed updates, right?
So
Yeah.
it works on both discrete and audio products.
Impala actually only works on discrete, I think.
But how do they compare with? Okay, A3C, right?
A3C, yeah. And another thing is, so this is another interesting thing, which I think would be sort of a interesting research topic, is that if you read this paper, what matters in non-policy reinforcement learning, it actually compares the off-policy laws that are being used, which, by all means, you would think something like Impala would have performed. So they compare something like regular policy gradient, compare with PPL, compare with vtrace, which is what's used in Impala. And as a matter of fact, vtrace performs much worse than PPL. So obviously, this is research done using sort of the PPL file structure, everything to run the experiments. But I wonder if this results extend to using the Impala kind of architecture. If it is the case that is being shown over here, then it might be very possible that Impala can be further improved by just using PPL-like objective instead of using its own developed vtrace, I guess.
Yes, that vtrace always gave me the yikes since Acer.
Huh?
That vtrace method is quite complex. So
Yeah. It's kind of similar to yeah, exactly like you said, like sort of like Acer. I think it's a little bit simpler than Acer.
oh, good. Yeah, maybe.
Yeah, but anyway, what else do I have in mind? I think that's basically all I have. Oh yeah. One last thing. If anyone is interested, my paper just got uploaded to archive. Basically, I investigate into the concept of invalid action masking, and I think I talked to Rosalind before, but my conclusion was incorrect. So the correct version is that invalid action masking actually produces valid policy gradients. Yeah. So invalid, for those of you who are not familiar with this technique, it's basically what AlphaStar and OpenAI 5 uses to mask out invalid actions. And they do it by basically saying, okay, I generate some logits, and then by using those logits, I generate a probability distribution. This is in discrete action space. And if I use this invalid action masking, I basically mask out the logits corresponding to the actions that are invalid. And it works by basically applying either an identity function to the logits or by replacing it with a very negative number. This is actually incorrect. This is M. I've already uploaded a newer version, but it should update on Tuesday. But either way, it's either an identity function that keeps the original logits, or it replaces the logit with M, which is a negative number for the invalid action. So as a result, this function is differentiable because an identity function is differentiable and a constant function is differentiable. And since they're differentiable, it follows the assumptions that are made by policy gradient methods. Therefore, it is a policy gradient. However, this function is a state-dependent differentiable function. So that's a very interesting results, because if you look at all of the policy formulation that are in existing work, it's always state independent, such as sigmoid, softmax, hyperbolic tangent. It's always some state independent differentiable function. But this is, I think, the first known state dependent differentiable function being applied to the policy formulation, yet it still works. And essentially, in our theoretical result, in our empirical results, we show that invalid action masking is actually really important, especially when the space of invalid action is large. So those are the main results. I'll be writing a blog post to sort of explain this paper, which hopefully will make the concept more accessible. But yeah, in case you're interested.
That's nice.
Yeah, no problem. My pleasure.
But this sounds kind of a niche technique in the end, like the invalid action.
Yeah, indeed.
And one question, because you mentioned that this techniques is superior to as it enables as can be used only with policy gradients, then policy gradients are superior to value-based methods, right?
I wouldn't say superior. It's just an alternative.
It's alternative, but okay, so it wasn't like you wanted to stress that they are better because
Well, my personal experience is that policy gradient methods are usually easier to use. Yeah. By the way, there doesn't seem to be a clear approach of how invalid action masking could be applied to value-based methods such as DQN or C51. So I think that may be another interesting research direction.
yeah, normally what you do is assign some infinity number, right? Infinity small number.
Yeah, I feel like that wouldn't work right away, but I could be wrong. All right. So thanks everyone for coming. Hope you guys have a good weekend. And so if anyone is interested in leading the next monthly development cycle or just having the next monthly meeting, let me know. And I'll let everyone else know so that we can have the meeting for next week. But otherwise, we'll probably see you next month.
Thank you and enjoy holidays.
Thank you.
Thank you. Yeah.
All right.
Nice weekend, everyone. Enjoy your holidays.
Nice weekend, guys.
Thanks.
Yeah,
See you. Thank you. Bye.
Bye.